Good afternoon. Welcome back, Johanna, to his next lecture, lecture 2.
Thank you very much. Yes, thanks. Okay, so let's come back to what I was saying yesterday. So today I'm going to redo everything I was saying yesterday, but slowly on the blackboard. Okay. So yesterday I said that the best understood example of gauge-gravity duality is the ADS-CFT correspondence. And the reason is because this has a lot of symmetry. So why is it the best understood example? So there's lots of symmetry. And so as I explained to you, there's a conformal symmetry, which is SO4, 2. So I should say global symmetry. So these are global symmetries. And then there was this SO6. Okay. And so the Lagrangian of the field theory is known. And so this was this NX24 SUN super Young-Mills theory. And and also the string theory brain construction is known. And this was involving the D3 brains. Okay. So all of this I would like to explain in more detail. And so let me start with the Lagrangian of this field theory quickly. So the fields of this NX24 SUN super Young-Mills theory. So SYM is the abbreviation for super Young-Mills. Okay. They are organized in one single super multiplet. So this is the super multiplet of the supergroup. So there's also something called a supergroup, which has a fermionic extension. And it's a fermionic extension of the group which involves this SO4, 2 and SO6. Okay. So, and let me write down what the super multiplet is. So since it's a gauge theory, it should start with a gauge field. By the way, is this big enough? Can you read this? Yeah, no complaints. Okay. So this is an SUN gauge field. Okay, and this is a singlet of this R symmetry, which is SU4R. Okay, and remember that SO6, so this geometrical symmetry here, is isomorphic to SU4. So it doesn't really matter if I write SO6 or SU4, so the generators are a very similar structure, the algebra is the same. And so I start with a gauge field, which is a singlet of this global symmetry. And then I can apply the ladder operators of this supergroup or superalgebra, and then I get all the other fields in this theory. So first, there are 4 complex fermions. So they are written like this. So these are viral fermions. So of course they are also in the adjoint of this gauge group because the gauge field is in the adjoint. And they are in the fundamental representation of SU4. Okay, and then we have 6 real scalars. So here A goes from 1 to 4, and this I goes from 1 to 6, and so I have 6 real scalars. And they are in the representation 6, which is the antisymmetric representation. Or the adjoint representation of SU4. Okay, so the key point is that all these fields are in the same multiplet, which means that there's only one coupling in this theory. And so I can write the Lagrangian okay, so this Lagrangian, okay, so there's a trace because it's a non-abelian gauge theory. And then I start with the kinetic terms. And so this is the gauge kinetic term, then there's a kinetic term for the fermions. Okay, so you sum over all these indices. This is a Pauli matrix. A covariant derivative. So here we sum over these 4 A's, and then there are 6 complex scalars. And so we have these six scalars. So this is the kinetic term for the scalars. And then there's a number of interaction terms. So first we have 2 Yukawa type terms. So they're cubic. Okay, so you have to sum over A, B, and I. And there's some structure constant, which I'm going to write down in a second. And so there's one fermion here. Then we have one of these scalars and another fermion. And then there's a complex conjugate of this term. G is going to be our coupling. And again, so since these fields are in the adjoint representation of the gauge group, they don't commute because we have a non-abelian gauge theory. And then finally, there's a quartic term for the scalars. And again, with the same coupling. And so okay, so these C's, they're just essentially Golden coefficients. That couple two representations, fundamental representations, to one adjoint representation of the algebra of SU4. Okay. So, and I closed the bracket. So, okay, so this is the Lagrangian of this quantum field theory, and so this is in 3+1 dimensions. And okay, essentially I want to emphasize this is a pretty normal quantum field theory. Okay, it's not exactly QCD, but it's in some sense it's quite similar. The only thing is if you calculate the beta function for this coupling G, you can show that it vanishes identically, and this is due to the supersymmetry. There will be some cancellations between all these interaction terms when you draw the Feynman diagram. Okay, so one important thing, and then I should mention, is the large N limit. So if we have this field phi, I mean, I should write the same phi as before. Phi. Okay, so this has an index I, which has the 6 Hilbert indices, and then so it's in the adjoint representation of the gauge group, so it's going to look like this. Okay. And so now, of course, this matrix is also going to have indices. So let me call, okay, sorry about changing notation. I think this is a bit confusing, but let me call this I capital A. If I don't do this now, I will make lots of mistakes later on. Okay, so think of these I's and J's as capital letters. This is just a renaming. And the reason I'm renaming this is because, of course, so this is a vector of matrices, but these matrices, they will also have indices, and now these I will call I and J. And well, maybe I should do it the other way around to be consistent with my notations. I and J. Yeah. Can I? Well, okay. So this is a non-abelian gauge theory. This is a kinetic term for a fermion. And this is a covariant derivative which involves the A which is in here. Okay. And this is a kinetic term for these 6 scalar fields. And again, these are the covariant derivatives involving this gauge field. Okay, so that's the kinetic terms. And okay, so this, since the theory is going to be, this theory does not have any mass terms because it's conformally invariant, so there cannot be any masses. Okay. However, there are some cubic and quartic interaction terms, and you can actually count that this coupling is dimensionless, so it's a renormalizable quantum field theory. And these terms, they're called Yukawa terms, and it's just a coupling between 2 fermions and 1 scalar field. And the reason there's this commutator is because these fields are in the adjoint representation, so they look like this, and these T matrices don't commute. Okay, so that's why there's a commutator. Now this term is just the complex conjugate of this to make the Lagrangian Hermitian yes, and that's because of the supersymmetry. The supersymmetry forces you to have all these couplings must be the same, because all of these fields are in the same supermultiplet. If you start putting different couplings, you break this SU4 symmetry. Okay, so this is a pretty strong symmetry, and this forces you that this coupling must be the same everywhere. And it's also the same. Should there be a squared here? I think probably yes. I think so. Does that answer your question? Okay, good. Yeah. Yeah. Well, so you can look at something called you can look at the water identity for the so-called supercurrent, which also involves the energy momentum tensor. And then essentially the beta function appears as the coefficient. And it also appears then because this energy momentum tensor and the R symmetry current are in the same supermultiplet. And then you can show that the divergence of the R current must be anomally free. And from that, you can, by supersymmetry, then infer that also the trace of the energy momentum tensor must vanish. And if you want, you can do it order by, you can do it kind of by induction, order by order in perturbation theory. But you can also show that instanton contributions cancel. And so, so I think this was found by Howe in West in 1981 or something. Okay, so one important thing is the large N limit. So, so we have these indices here, so we can write the propagator. So now, okay, I put these 2 indices here. So where essentially I pull this matrix back into this field, and so I have these. So these are the matrices of the adjoint, the indices of the adjoint matrix, and so if I have a propagator now in configuration space, so this is a vacuum expectation of a time-ordered product, then I can essentially show that this will take this form. So there's just two Kronecker deltas. There's g squared, and then there's 4 pi squared x minus y squared. Again, I'm still in 3+1 dimensions here. And okay, so and that suggests actually, that's why Tuft introduced this so-called Tuft coupling lambda to consider an expansion in this form, because okay, so here essentially I have calculated the product of two of these matrices using fields identities, so I have to calculate this. Okay, and so normally there would be subleading terms. So there would be something with a 1 over n and then other Kronecker deltas. But since n goes to infinity, I can just drop those. Okay, so this is only true for n going to infinity. Okay, and so then it's convenient to introduce a double line notation for these Feynman diagrams. So essentially, for one propagator, you draw two lines, and so the momentum just, so say your momentum flows in this direction, but then you take the index I to L, on the other hand, you take K to J. And you see, so you have this oriented line. And then, so as Tuft showed, if you write the perturbative expansion now in terms of the lambda, okay, so lambda, the so-called Tuft coupling. And if you do that, then your Feynman diagrams will, so imagine you have two vacuum diagrams, okay? So one vacuum diagram which looks like this. Sorry. Oh, I got too close to the speaker. So if I have a vacuum diagram like this, if I draw this in this double line notation, it's going to look like this. Okay. It's not very beautiful, but I hope you get the idea. So it's like a no parking sign. And then these lines are oriented. Okay, they're oriented the other way around, like this. Okay, so, but the key point of this diagram is this is a planar diagram. Okay, so then this diagram is non-planar, so there will be a crossing of lines. So in the sense that okay, the propagator here will try to make this. So essentially, this propagator is behind the other one. Okay. So essentially, then I have one line here, and this is also a closed loop. I can go here, then underneath, around here, along there, back here, and then underneath here again, and here, and then there. Okay, so this is one connected line. But this, so it's non-planar because, well, obviously the one line is behind the other one. So you need so this is non-planar. In the sense it needs the third dimension. So, and now if you do for a perturbative expansion, in lambda, which is G Young squared n and n, then for n going to infinity, only the planar diagrams contribute. Because you can show, if you write down the Feynman rules in this expansion, that these diagrams they have some order. They have a prefactor 1 over n squared compared to this diagram. So if you send n to infinity, then this doesn't contribute. Okay. So when I say the planar limit, it means we'd only have to consider these diagrams, and that's precisely the limit when we can neglect all the quantum corrections on the gravity side of the duality. Okay, very good. So I reached the end of the blackboard, so let me go back to the other side.
So the 2-point function falls off at 1 over x squared, like behavior, right? So it's also said that in CFT there are no asymptotically free states.
Oh no, this theory is not asymptotically free. It's conformal.
What I mean is that there is no concept of ace matrix. I mean,
It's not what?
Concept of ace matrix in conformal field theories.
There's no concept of an S matrix. Yes, exactly.
So even at far infinity, the states are not actually free.
Yes.
So is it because there's this power law fall off instead of exponential fall off, something like that?
Okay, that may be the case. Very good question. I didn't quite expect. Well, okay, so the conformal symmetry dictates that you have this polynomial behavior.
Exactly.
And certainly that's tied to the fact that you don't have an S matrix in the theory due to the scale. I mean, due to the scale invariance, it's very hard to say what an asymptotic state is.
Right. I mean, it's we have to contrast it with the exponential fall off.
Yeah, exactly. That's completely right. So later, I mean tomorrow, we're going to break the conformal symmetry, and because in the end I want to study QCD or QCD-like theories, and then once we break the conformal symmetry, then we go back to all the formalism which you know. Okay. So then we won't have these particular. These propagators were particular to NX4, but a scalar field in a conformal field theory. But okay, this is just for the sake of the ADS-CFT correspondence. Okay, let's understand a little more detail where the ADS-CFT correspondence comes from. So as I said yesterday, ADS-CFT is a conjectured duality between precisely this quantum field theory I've just written down and a particular string theory, which is called 2B superstring theory. So it doesn't matter right now what 2B means. It's just a name of a particular string theory with some particular fields involved. Okay. And this theory will be on ADS5 times S5. So this I also explained yesterday, and then we see again where our symmetries, so far the symmetries I discussed were symmetries of the fields in the quantum field theory, but now these same symmetries here, they are symmetries of the geometry. Now here they are realized in a different way. So the conformal symmetry shows up as the isometries of ADS5, and then S5 has an SO6 symmetry, which again is isomorphic to SO4. So here in this geometry, I have the same symmetries as before for the quantum field. Okay. So now, as I said yesterday, also. It's not really well understood how to quantize this theory in a curved space background, okay? So this is a very beautiful statement, but maybe it's not really super useful at present because we cannot do any calculations in this theory as of the present day. I mean, maybe someday somebody finds out how to quantize strings in first place backgrounds, and then we can also prove the ADS-CFT correspondence, but it's not so easy to do. So the idea, which I also mentioned yesterday, was to take some particular limits to reach some theories which we know and where we can do calculations. Okay. And there will be a series of different limits, as I also mentioned already too. Yesterday there will be 2 limits, and and also yesterday somebody asked about in what parameter regime we are. So I will also answer this question now in the subsequent. Somebody sitting about here asked yesterday, so with your duality you have to take particular regimes of the coupling. This will show up in 1 minute. So the first step towards understanding these limits is to consider a weakly coupled string theory. So if it's weakly coupled, it means the string coupling is much less than 1. And on the other hand, we keep the ADS radius divided by the square root of the string tension. This we keep constant. So essentially, the square root of the string tension you can consider as being the length of the strings. So also, as Ayan asked yesterday as the very last question before we finished, so then the leading order is classical string theory. You did. No, but before we. Okay, so as Ayan paraphrased Raji's question yesterday, well, this was the question which we just discussed at the very end of the lecture was, so what's actually this limit when I take GS to be very small? Then the leading order is classical. Okay, I just wanted to allude to the fact that we did this yesterday at the very end. Okay, then this classical string theory, so that's what we expand about in this case. And so classical string theory means that the string coupling vanishes. Okay. So yeah, L is the ADS radius and LS is the length of the string. Yes. Okay. Okay. So on the CFT side. So now, yesterday I wasn't very proper, so I dropped a particular factor of 2 pi, which I now put back in again. So we write 2 pi GS is G Young-Mills squared. Yesterday I was sloppy, I just said GS is G Young-Mills squared. Maybe even over there I did this again, but this factor of 2 pi will now be absorbed. Okay, so taking this limit, GS being very small, this implies that if G Young-Mills squared, which in our large N expansion we write as the TÜV coupling divided by lambda. So if GS goes to 0, then G Young-Mills squared also goes to 0. And then this goes to 0, but if we keep this lambda fixed, this then really means that N goes to infinity. And okay, so let me stress that lambda is kept finite. Okay, and I should say also we note yesterday I already discussed that actually 2 lambda will be L to the 4th over alpha prime squared. So and so this limit is the limit which TÜV used for the large N theory. So this is the limit where only these planar diagrams contribute. And so we recover this here. Okay, so essentially then what you see here is that an expansion in 1 over n corresponds to an expansion in this GS. Which means that there's an equivalence of doing an expansion in string theory and doing an expansion in a large N field theory. So essentially the stuff I did over there, okay, fortunately I didn't rub this off. So if I have this propagator here, which I rub off, I mean, this was just a double line notation in large N quantum field theory, but I can identify this with a propagator of a string, okay? So it's an extended object which propagates in this direction. And then, so somehow these field theory diagrams look like diagrams of string theory. Okay, so in some sense you can say a large N gauge theory is equivalent to a string theory. But the problem is, with the information I gave you here, it's very hard to say which string theory is equivalent to which large N theory. You know, there's just a formal resemblance of the Feynman diagrams, but it's very hard to say to which theory these diagrams correspond to. But this is just what ADS-CFT is going to tell us. So ADS-CFT will enable us to make this map very precise and say, okay, these string theory diagrams correspond to an expansion about this particular quantum field theory. Okay, so, and that's where all this huge symmetry is going to help us to really make this identification concrete. Okay, yeah.
Okay, so I have read that, so there is something about the radii of ADS and of S5. Okay, yeah. In this case, probably they're equal, but I think there is another example of the conjecture which probably you'll show for QCD when the radii of ADS and the compactified manifold are not equal.
Yes, okay. I think as we will see later on as we go along, the construction which I'm going to show to you now shows you that the radius of the ADS space and the radius of the S5 will be the same. Okay, so, and that comes because we start from some particular string theory metric, and then we take this limit which I'm discussing, and there's only one scale, so the scale is everywhere. Now, later when we do QCD, we won't have an S5 because we need to break the supersymmetry. We will have something squashed and so on. So I'm not sure if we can even define just one scale easily. I mean, we have to look at particular examples to understand. I mean,
the ADS7 cross S4.
Okay, that's another example, but this has nothing to do with QCD. This is another example. So, okay, this is a good question. So far, I'm telling you the best understood example of the ADS-CFT correspondence, which involves this NE4 super young Mills theory, and then has an ADS5 times S5 space. There are other examples of ADS-CFT where you have supergravity solutions, so that's what I'm coming to now, and where the supergravity solutions are not ADS5 times S5, but they are ADS4 7 times S4, or they are ADS4 times S7, for instance. In that case, you know, if we have an ADS4, it means our field theory is in 3 dimensions, and if we have an ADS7, then it means our field theory is in 6 dimensions. But for the 6-dimensional case already, it's not really clear how to write down the Lagrangian. I mean, in ADS4, I mean, you can write the Lagrangian, but it becomes a rather exotic quantum field theory. It's called the ABGM theory in 2+1 dimensions. And so, yeah, you're absolutely right. We can write dualities for these theories, but they take us away from QCD. I mean, my aim is QCD, so I should better stick to 3+1 dimensions. Okay. These other examples, they're beautiful, but yeah, I think they are of more mathematical interest. And you know, I'm still heading towards applications at the end, so I want to be in 3+1 dimensions.
Okay, so in this case, the radii of ADS5 and S5 are taken equal.
Yeah, they will be equal, and maybe if you wait for 15 minutes, you will see why they will be equal. Okay, so that's, I'm heading to explaining this. Okay, well, maybe 20 minutes, but it will be said today why the radii will be equal. Okay. Okay, good. So as the question was already alluding to, I should show you how to solve supergravity and to get this ADS 5 times this 5 metric. Okay, so that's what we're having to. Okay. Okay, let me get back to where I was. Okay, so I made this comment of mapping quantum field theory diagrams to string theory diagrams. And so the upshot was that the 1 over n expansion in quantum field theory can be mapped to a string genus expansion for fixed lambda. Okay, and so this limit is known as the strong form of the ADS-CFT conjecture. And so there's also a weak form in which additionally has the limit that we take lambda to be large. So it additionally involves the limit that lambda, as I defined, is also large. And then this means we have a strongly coupled quantum field theory. But in view of QCD applications at low energies, that's exactly what we are after. Okay. So in this case, in the weak form, a strongly coupled quantum field theory is coupled, or is mapped to a supergravity theory of point-like particles, because in this limit, essentially the string length also goes to 0. So and if the string length goes to 0, it means our string becomes a point particle. And then in this example, sorry, I have to sleep. Sorry. In this example, the gravity theory is a 10-dimensional gravity theory, and it's called type 2B supergravity. So the name type 2B supergravity comes from the fact that before we had type 2B string theory, so we just take the length of the strings to 0. Well, I didn't tell you what a type 2B string theory is, but it doesn't really matter for the purpose of this lecture. It's just the name of this theory. Yeah? Yes. Yeah, okay, so, okay, I took a slide shortcut here. So, I mean, you can take an intermediate step. Okay, so the strong form is that you allow for GS to be non-zero. Then this intermediate form is when you take n to infinity, but lambda can be any value, and then you can map perturbative quantum field theories to classical string configuration, so that leads to this integrability. And then the third limit is this weak form, where we take both lambda and n to be big. Okay. Okay, and the key point of this theory is that this type 2B supergravity admits these three-brane solutions. So already yesterday I said that these three-branes are super important for formulating this example of ADS-CFT. Okay, so yesterday I already told you a few things about these three-branes. So again, let us now consider these three-branes to motivate the ADS-CFT conjecture. Okay. So, and as I also mentioned yesterday, these three-branes may be viewed from two different perspectives. And so one was the open string, and the other one was the closed string perspective. Okay, and as I explained yesterday, rather heuristically, this will lead to a gauge theory, and this leads to gravity. Okay. Okay, so now what I'm going to do is I'm going to explain a little more these two perspectives in detail. So first I explain a few things about the open strings. Then I explain a few things about the closed string perspective on these three-branes. And then finally we will bring everything together. Okay, and then we have the correspondence. So let me start with the open string perspective. So again, so somebody yesterday asked about the precise limits which we take. So now let's look at GSN being small. Okay, so that's the open string case. So then in this case, the D-branes may be visualized
One question. The starting point for this duality was basically the resemblance between the Feynman diagram of quantum field theory and the string theory, or was there some other basis also from which it actually started? I mean, you said that there were other results which was proved to be correct, but that came later on. What was the starting point of this? Like,
well, this is exactly what I'm going to explain. Can you wait for the end of the lecture, because this is what I want to explain now. Okay, so okay. Unfortunately, it was going to take about half an hour, but the next half hour will be precisely the answer to your question. So the question was, how do we motivate the ADS-CFT correspondence other than string theory? And okay, just hang on for 30 minutes and then I will come back to this point. This is exactly the question you should have in mind and when you follow what I'm going to say now. Okay, so maybe I just said it. Yeah, okay. Here, let us now consider these three-branes to motivate the ADS-CFT conjecture. Okay, so I'm now going to motivate the ADS-CFT conjecture other than the, okay. So the difference to what I said before is that before I allowed for this case that n wasn't infinite. You know, there was this, I looked at this genus expansion, there was 1 over n. But now in everything I'm going to do, n has to be thought of as being taken to infinity at the end. Okay, so that's maybe the difference, because later I will talk about supergravity. For the time being, okay, let me just go on for a while. I will come back to this, but this is exactly what I'm trying to address. Okay, so let's consider this case. Then in this case, the three-branes may be visualized as higher dimensional charged objects on which open strings may end. I think I said that yesterday also. I had some pictures. Okay, so as I said yesterday, this D stands for Dirichlet boundary condition. Okay, so now what we're going to do is consider a stack of n coincident three branes embedded in 9+1 dimensional flat space-time. Okay, so we can draw this. Okay, so if you remember the picture I had in my slides yesterday, so we have this stack of MD3 branes, and then we have open strings attached to the stack. And then, so let me write the number of dimensions. So 0, 1, 2, 3 will be our real world, and then we have these extra dimensions, which will correspond essentially to some field theory degrees of freedom later. Okay, so, and then now we put these three branes. And this just means that now we impose Neumann boundary conditions in these directions and Dirichlet boundary in those. Okay, so n. Okay, so now there's a particular action which describes the motion of these open strings, and so these strings are described by a particular action, and the action is called the Dirac-Gluon Infeld action. Okay. So what is this action? So Born and Infeld, they already in the early 20s after Einstein, they tried to find a unified theory of electromagnetism and gravity. And so they developed the bosonic version of this action in this context. And then Dirac, well, it means, I'm not sure if Dirac did that himself, but this is about adding fermions to this action. So essentially, this Dirac-Gluon Infeld action is kind of a generalized string action for these three branes. And it essentially tells you, if the charge is set to 0, it just essentially tells you the minimal area which a particular surface in 10 dimension will fill. So you can also write a Born-Infeld action for a soap bubble. Okay, so if you have a Born-Infeld action in 3+1 dimension in flat space, essentially it will tell you that the soap bubble should be round. Okay, because that minimizes the energy. And here, this is now the kind of generalization of this concept to higher dimensions and also to charged objects. Okay. So let me write this Dirac-Gluon Infeld action. Okay, so there's a prefactor which reads 2 pi cubed alpha squared gs. So this whole thing essentially is the tension of the 3 brane. Well, this you can call T3, so it's tension of the D3 brane. Okay, so that's why there's my analogy to the soap bubble. And then because we can have another abelian charge, again, there's a trace. And then a D3 brane is an object in 4 dimensions. So I have an integral d4x. And then there's a term here where this phi is now the dilaton. So there's some supergravity fields. And then, so normally we, if you calculate the area of a soap bubble, you need the Jacobian. And the Jacobian is the determinant of the metric. And this determinant of the metric we will also encounter here. But now there's a slight catch because we need to calculate the so-called pull-back, okay? Because we have a 10-dimensional metric, and we want to calculate the pull-back to the work volume of this these 3 branes. So it's this P pulls back our 10-dimensional metric to this 3 plus 1-dimensional volume. And now, because the whole object is charged, there will also be a gauge field here. Okay. And okay, so if we switch off the charges, then we just left with the square root of metric, and so that same what you take to calculate this area of a soap bubble in flat space to minimize the energy. Okay, so now because it's Dirac, it means there will also be fermions, but I won't write those explicitly. We shouldn't forget there will be also fermionic contribution to this action. Okay, that looks somewhat complicated, but now this will very quickly bring us back to our NX24 super-Young theory, which I introduced at the beginning of this lecture. Okay, so now we consider a low energy limit. So remember, the whole point of this lecture is that I'm going to tell you what limits, okay? Limits. So this you have to keep in mind all the time. I'm going to tell you what particular limits, and here now we're going to take a low energy limit of this complicated action. And essentially, so the limit we are going to consider is low energy excitations so this means that the energy will be much less than the inverse string length, which we write in terms of this string tension. So where in this case only massless excitations are taken into account. And so the fabulous result now is, I hope you will just believe me, but I mean, you can do the calculation yourself. If we do this low energy limit, this action will exactly reproduce the action of NX24 super-Young theory as I wrote down at the beginning of the lecture. Okay, the gauge field is already here, and then the fermions we won't consider here explicitly, and this pullback will give us our 6 scalars, okay? Because we start with a 10-dimensional action, and we pull it back to 3 plus 1 dimensions. This means we have 6 embedding coordinates. And these 6 embedding coordinates give the 6 scalars in this action, which I wrote for you at the beginning of this lecture. Okay, so it's a somewhat complicated calculation, but I hope I gave enough information that you believe me that if we do this approximation, this Born-Infeld action of the brain just exactly gives us, or Dirac-Born or NX4 super-Young-Mills action.
I just had a question. So it happens even, so you haven't written the B field, right?
Oh, yeah, so I can, in this case, I can set the B field consistently to 0. So if I write down the equations of motion, I should write B field originally, but then if I write the B field and write down all the equations of motion I get for this action, I see that in the simple case of the D3 planes in flat space, B equals 0 is a consistent solution. So that's why I don't talk about the B, and I can simplify it right from the start.
I mean, when you say that n equal to 4 super-Young-Mills will emerge from this action, that is with the B or without the B?
No, without the B. I mean, no, you don't need a Nibble. You can just set the Nibble-Schwarz form to 0, and there's no. I mean, you know, the Nibble-Schwarz form will be 0, and in that case, this action will give precisely action of NX4 super-Young-Mills. But everything is consistent. All those equations of motion are satisfied. Okay. Later, if you want something more complicated, like there's some QCD models where you do have to take this B into account. If I start breaking, it's only so simple because I allow for lots of symmetries. If I don't do that, then I also have to worry with the B. But in this simple example, it's so simple that the symmetries allow it to set it to 0 consistently. But it's a good point. I mean, if later you look at more complicated examples, you have to worry about this issue. And just in this simple case, we don't have to. Okay, so the pullback gives us these 6 scalars. And so if you do the calculation, you get exactly what I'm writing on the blackboard right now. So can somebody read to me how the sentence started, and then I don't have to walk? What was my last sentence? Okay, very good, thank you. So in this case, the DVI action for these 3 branes reduces to the 3+1 dimensional field theory action for n equals to 4 SUN super-Young-Mills as discussed at the beginning of this lecture. So the 6 scalars arise from the pullback. Okay. So this means that the limit we are considering, so in the limit when alpha prime goes to 0, which also means that the string length goes to 0, the open strings decouple from any closed strings which might be around. From any closed strings or closed string excitations in the 10-dimensional space we started with. And we have that, so the limit alpha prime going to 0 of this dBi action is the action of NX4 super young mills, subject to identifying the string coupling with the young mills coupling. G young mills squared with GS. In fact, 2 pi. Right. Okay. Okay, so we have to be a little careful because we take a dimensional object, so a length to 0. So note this limit is taken keeping, or so we take any length scale, for instance, our anti-de Sitter radius, or just R any length scale fixed with R any length scale. So this limit will be important in a few minutes, and so this is referred to as the Mallar-Sena limit. Okay, before we had the 't Hooft limit, and now we have the Mallar-Sena limit, and so this is, the 't Hooft limit takes us to this intermediate level of the ADS-CFT correspondence, and the Mallar-Sena limit then takes us to the weak form, which I'm discussing. Okay, so let's get back to the logic of what I'm explaining. So I said, okay, again, let us now consider these rearrangements to motivate the ADS-CFT conjecture. So then I said there's 2 different perspectives, open string and closed string. So now I explained to you the open string perspective, so here we can put a tick, okay? Okay, so the next thing is I'm going to explain this. And the third thing is then I explain the relation between the two, okay? So now let's go to the closed string perspective. Okay, so now we take the other limit. So this is the limit when GSN is much larger than 1. In this case, the ND3 branes may be viewed as massive charges objects. So remember yesterday I told you about the tablecloth in the pumpkin. So this is, we're coming back to the story. Massive charged objects sourcing various fields of type 2D supergravity. And so the closed strings will propagate in this background. Okay. Now let me tell you, so I'm saying these branes, they source these fields, and you can actually write them as a solution to the Einstein equations, which you get from this type to be 10-dimensional supergravity. Okay, so it doesn't matter what type to be supergravity is, I'll just tell you it's a particular gravity action in 10 dimensions, which in addition to the metric has some extra fields. And so yesterday at the very end I said that once you have a gravity action, then you can calculate the Lagrange equations for this action, and these will be the Einstein equations. Okay? So then you have these 10-dimensional Einstein equations, and then these will be second-order differential equations, so you can make an ansatz to solve these equations. Okay, so and these three branes now, there will be a particular ansatz for solving the supergravity equations. Okay, so the supergravity, supergravity solution of n d3 branes preserving SO3, 1 times SO6. So now this is the Lorentz group in 3 plus 1 dimension. So, okay, so this will be a solution embedded in flat 10-dimensional space. So flat 10-dimensional space is R9,1. So now let me tell you what this ansatz is going to look like. So first, we have an ansatz for the metric, and there will be some arbitrary function h of r in this ansatz, which then, if we insert the ansatz into the Einstein equations, there will be an equation determining this h. And then here, eta mu is our Minkowski metric in 3 plus 1 dimensions. And then we have another contribution. So there's the same function h of r to the power a half now. And so this is for the 6 coordinates which are perpendicular to this 3-dimensional brane. Okay. So essentially this r is a radial coordinate perpendicular to the d3 branes. So this will be x4 squared plus x5 squared plus x6 squared plus x7 squared plus x8 squared plus x9 squared. Okay, so this is this radial variable in the 6-dimensional space. Okay, so but the supergravity doesn't just have the metric, there's more ingredients. So first of all, there's this dilaton, and the dilaton will have to coincide with the string coupling. And then, as I said yesterday, in these supergravity actions, you have these higher order gauge fields, and there's going to be a particular 4 form, which essentially looks like this. So it has d naught wedge dx1 wedge dx2 wedge dx3. Okay, so this is also part of the supergravity theory. And then you can define a 5 form, which is a generalized gauge field, as an exterior derivative of this 4 form. So this is all very similar to electrodynamics in 3 plus 1 dimensions, just with more indices. Okay, so this is an ansatz. And now we plug this ansatz into the equations of motion of the supergravity theory. Okay, so maybe it's all a bit difficult because I'm talking about 10 dimensions and supergravity, but essentially we do what you learn in your 2nd year undergraduate. We write down the equation of motion, we make an ansatz, and we solve them. Okay, so this is just Lagrangian mechanics. I mean, nothing fancy as far as conceptual things are concerned. Okay. So, so now we insert, so this is my ansatz. So it has 3 parts. It has this. Okay, so I think this is the most important. Maybe I should put a line around this. Okay, so I have one factor depending on this radial variable in front of the Minkowski part, and another factor with the opposite sign here in the 6 directions perpendicular to my d3 branes. Okay, so is that still my table? Okay, okay. So for these directions, so this is where this x coordinates, so x mu coordinates are in these directions, and the xi they're in these directions. Okay. Okay, so now we insert this ansatz. Into the equations of motions of 10-dimensional type to be supergravity. And if we do that, especially the Einstein equation will imply that Laplace operator acting on this function R has to be 0 for R not equal to 0. So Laplace with respect to this metric G. And so this means that H has to be a harmonic function. And so this means that, so this equation is satisfied either if H is just a constant, so we can take this to be 1, or if it is L over R to the fourth. So that's a solution to this equation. And okay, so L at the moment is just a length scale, but this will turn out to be somebody, you asked this, okay. But now, what I will do now is I take this ansatz and I plug it back here. And then I take a particular limit, which will give me ADS 5 times this 5. And L will be the same for the radius of the ADS and the S5. Okay.
Similar analysis can be done for any
Yeah. If I do the same for ADS7 across S4, I just start shifting some coordinates from here to there. Okay. Yeah. Okay. So this L is just a scale, but in fact, L may be determined from string theory. And in fact, one equation which has to be satisfied for quantization of charges is if you take the 10-dimensional Newton constant and you integrate, you put a S5 sphere at infinity around these three branes. This is a kind of generalized Gauss's law. So if you integrate over the field strength, you should get the total charge. But now the field strength is this complicated gauge field. This one, okay? So I have, in the supergravity theory, I have this complicated 4 form, and then this gives me the field strength tensor. And if I integrate over this, then this should be equal to n, which is the charge of my these three branes. Okay, and now if I calculate F5 with this ansatz, and then integrate over a 5-dimensional sphere, and okay, essentially this equation is Gauss's law. And then this equation implies something which I had yesterday already, that L to the fourth has to be 4 pi gs n alpha prime squared. So, and this is a super important equation because, so here's our TÜV coupling. So if I divide this equation by alpha prime squared, then on this side I have the TÜV coupling, and the TÜV coupling will be related to the ADS radius divided by the inverse 10 strings tension squared, okay? And then the limit will be to take alpha very small by keeping the L fixed, which then means that lambda has to be very big. Okay, I have 3.5 minutes. If I get 1.5 minutes more, I will just finish this calculation, because then next time I will come back to the question which was asked earlier. Okay, very quickly, let's take this limit, the low energy limit for the solution which I just showed to you. Remember, I'm talking about closed strings now. Okay. Okay, so, and so if we now consider the asymptotic regions, So then there's two. One is when R is much bigger than L. So if R is much bigger than L, I can forget about this term, and then H is essentially equal to 1. And if H is equal to 1, then I have flat space. And the other region is when R is much less than L. And in this case, it's the opposite. Then this term becomes very big, and then I can forget about the 1. Okay, so in that case, essentially, H of R will be L to the 4th over R to the 4th. And so this, for reasons which will become clear shortly, this is called the near horizon region. Okay, so then if I insert, now this case, if we just insert into the ansatz for the metric, then we get the following. We get ds squared is r squared over l squared eta mu nu dx mu dx nu. So I just replace this h by this, okay? And then similar here at the back, we have l squared over r squared delta ij dxi dxj. Okay, then now to conclude, we define a new coordinate z, which is L squared over R. And so if I do that, then I can regroup things a little differently, because I can write this here. I can essentially write as dr squared plus r squared d omega phi squared. Okay, so these are 6 coordinates in flat space. So I can introduce polar coordinates in 6 dimensions. Then I get this. So these are 5 angles and 1 radial coordinate. So, and then if I do this coordinate transformation, then what I get is L squared over Z squared eta mu nu dx mu dx nu plus dz squared. So I now regroup this r, dr squared together with the first 4 coordinates, and then plus L squared d omega. Oh, super, I'm really just on time. It's my last equation. Okay, for today. D omega 5 squared. Okay, so now can somebody tell me what this is? Okay, so what is this? Yeah, okay, so it's the metric of ADS 5 times 5. Okay. Okay, so to summarize in 1 minute, I showed you the open string perspective, and this was this one infinite action, and then we said, okay, let's take a low energy limit, and in this low energy limit, what we got was, on the one hand side, we got the field theory action of NX24 super young Mills, okay? And there might also be some closed strings in the 10-dimensional space, but they decouple, okay? So there's no interactions between this NX24 theory and these 10-dimensional degrees of freedom anymore. Okay, then I showed you the closed string perspective, showed you the ansatz for the metric, and we also take some low energy limits, and that's what I will tell you tomorrow, because these low energy limits can actually be identified with the low energy limits in the open string perspective. And in this low energy limit, which corresponds to this near horizon region, we get the metric of ADS 5 times this 5. Okay, so tomorrow, the first thing I will show you, and that will answer your question. I will show to you, and this provides further motivation for the ADS-CFT correspondence, that I can identify the low energy degrees of freedom in the 2 pictures. and how I will explain tomorrow. But the key point is, so in the open string picture, if we take the low energy limit, we get NX4 superyoung mass theory. Here, if we take the low energy limit, we get the space ADS 5 times its 5. Okay, and tomorrow I will explain, motivate how these can be related based on everything I just said. But I think the answer to your question from 1 hour ago, I'm 90% there now. So, tomorrow I just have to identify the two things, and then this will provide further motivation outside the direct context of string theory. Okay, thank you very much. So any questions?
Yeah, I had one.
Excuse me. Over here. Yeah. So this is a metric of ADS in the Poincaré patch, which only partially covers ADS. So why don't we get the whole metric of ADS?
Excellent question. So I got asked. So my student asked me the same question yesterday. It's a very good question, but I think if you start with this answers for the D3 brains, you essentially just get the cover, half of the ADS space, and then you have to continue to the global space. Right, it's a very good question. I think generally people assume that you can do this continuation without problem. But you are absolutely right. What we get is the ADS metric in the Poincaré patch, which only covers half of an anti-de Sitter space. That's correct.
Yeah, I had a question. So in this open string picture, okay.
Yeah.
So you say that when you take this alpha prime goes to 0 limit, the open string and the closed strings decouple from each other.
Yeah.
So, but what my question is that in order to get super-Yang-Mills action from DBI, don't you need this alpha prime goes to 0 limit even there also?
Sorry, say the last sentence.
So to get the super-Yang-Mills action
Yes.
from this DBI action,
Yes.
don't you need to take this alpha prime goes to 0 limit there as well? I mean, I say this because so super-Yang-Mill has got this f squared term, right? And here you have a square root determinant 2 pi alpha prime f.
Yeah, but maybe I wasn't super clear. I mean, okay, sorry. I mean, you're absolutely right. So this action you get from this action by taking alpha prime to 0.
Right.
Yeah, sorry if this wasn't clear. Yeah. You're absolutely right. Yeah.
So another thing is that, so the other instances of ADS safety that you just mentioned,
Yeah.
so the gauge theory action also similarly follows from this DBI for those cases as well?
For other examples.
Yeah.
Yeah, but it's not so obvious. Well, okay. So for ADS 4 times F7, yes, you can do a very similar construction. And then, you get the so-called ABGM theory.
Right.
Well, there's some, it's a little more subtle because it's not an action in flat space. You have some complicated background, but the idea is the same. Now, for ADS7, it's a bit more complicated because there is no renormalizable gauge theory in 6 dimensions. And, I mean, of course, in principle, you can do this calculation, but then you get something in the recoupling regime. But ADS CFT correspondence maps then to the strongly coupled regime. And since the theory is not renormalizable, you don't know what the RG flow is, and it's all less clear.
Thank you.
Any questions?
Yeah, let me just to follow up on this very quickly. So I really should say that the 3 + 1 dimensional case is really special because, the beta function is 0. And so the weakly coupled theory and, the strongly coupled theory, they're still, essentially very closely related to each other. Any other examples where the beta function is non-zero, then of course this map is far less obvious. And so in this example, many things come together which make it super clear. Okay. Sorry, where are you?
I think this is for D3, this is self-dual. This also has something to
Yeah, that's another thing. I mean, the fact that you get the self-dual form, and also in the D3 brains, the dilaton doesn't run, which exactly corresponds to the fact that beta function vanishes if you take D8 brains or well, I'm in the wrong direction. If you take the 7 branes or say the 4 branes in type 2b, then the beta function runs, and type 2a, sorry, then the beta function runs and it's a lot less clear what's actually going on. Because in the end, you have to compare the gravity to the strongly coupled field theory. Here, I'm telling you how to get the weakly coupled field theory.
No questions, I guess. So let's thank you for the lovely talk. Thank you.